Hello ma'am, hello guys. I'm Sherwin Razon and my topic is all about centroid, composite area, parallel axis theorem, product, inertia, and moment of inertia. Thanks for watching and let's get it on. Hello guys, I'm Sherwin Razon and our topic is all about centroid. So, this example is trying to use an integration method to find out the centroid for the curve. So the equation for integration is the x bar and the y bar. So we have an example. First, we have to draw the vertical rectangular. So this is the vertical rectangular to do the integration. In order to do the integration, we need to find out what is the little area for the rectangular. This is the little area of the rectangular, the point. You just draw and then what is the x tilde and y tilde. So the definition for the x tilde and y tilde is the centroid. So this is the x tilde. That's why the point. So again, the centroid of the little rectangular is I just draw on the picture. So this is the little. In this picture, what we can have is how we are going to calculate the little rectangular area is the base times height. The base times height. So the base will be the dx. This is the base, the dx. And what is a height? What you can know is the point on the curve. The point on the curve will be x and y. So which means the dA is equals to the base is dx and the y and the height is y. So you can see this point is the x tilde. So since we draw the little rectangular as small as possible, so that's why the x tilde for the vertical rectangular will be x. And what about the y tilde? You can see it's halfway. It's in the middle so that it's halfway of the y. So that's going to be y over 2. Since we are doing the integration over the dx here, so it will be better to change the y to x form. So this is the x form. So now the next thing to do is to decide what is the integration domain for this equation. So you can see, since we are using the vertical rectangle, so it's going to be kind of go all the way up till the end. So that's why our integration domain will be 0 to 4. So let's solve it carefully. So finally, we got our final answer, which is 2.5 inch. And the same thing for the y bar here. So we go back to the picture so that you know if this makes sense on that. To check all your work, so we can see the x bar will be 2.5. The x bar will be 2.5 here, and we go a little bit here. It's right here or somewhere here. It's not outside of the shape, which means you've done a good job. Hey guys, I'm Sherwin Razon, and our topic for today is all about composite area. So magta-taglist lang tayo ngayon guys, so para mas maintindihan natin. Okay. Ito yung sketch sa composite figure. Then, i-find natin yung area niya. May tatlong step lang tayo para makuha natin yung area niya. So, first step is to decompose the shape. Second, find the individual areas. And the third is add to find the total. So, ano ba yung makikita natin dito guys para ma-decompose natin ang shape? Ma-decompose natin itong sketch na to. So, kuha lang tayo ng ballpen natin or pen. At sa tingin nyo guys, ano yung makuha natin na shape sa figure na to? So, tama, triangle. I-sketch lang natin yung point dito hanggang dito. Sketch lang natin guys. So, may shape na tayo na dalawa guys. Isang rectangle at isang triangle. So, rectangle and triangle. First guys, kukunin natin yung area nitong rectangle. Rectangle ito guys ha. So, area of rectangle is equals to base times height. So, paano natin makuha yung base niya guys? Base ng rectangle. So, yung distance nito at saka distance nito at saka distance nito at saka distance nito is pareho lang guys. So, yung distance nito 16 guys, no? 16 to 16 centimeter. So, kaya yung base niya is 16 centimeter times yung height niya guys. Height, yung kataas. Yung height niya nito. So, 8 centimeter. So, 16 times 8 is 6 times 8 is equals to 16 times 8 is 128. So, 128 centimeter square. So, ito yung area ng ating rectangle guys. So, ngayon guys, nakuha natin yung area ng ating rectangle. So, 128 cm squared. Susunod na step is kukunin natin yung area ng ating triangle. Ito yung triangle guys. So, area of triangle is equals to base times height divide 2. So, paano natin makukuha yung base niya guys? Itong base nito dito. Dito niya guys. Itong point dito at saka point dito, itong distance dito, diba 26? Tsaka yung distance dito at saka distance dito, isa-subtract lang natin guys. So, 26 minus 16 is equals to 10. So, ang base dito guys, ng ating triangle is 10 cm. So, 10 centimeter times yung height niya guys, yung height dito at saka ito, pareho lang yan siya guys. So, 8 centimeter divided by 2. So, equals 10 times 8 equals to 80 centimeter divide 2 40 centimeter squared na yan guys ha, squared. Ito yung ating area ng ating triangle. So, ito na guys. So, nakuha natin yung area ng ating rectangle. So, 128 at saka yung area ng ating triangle na 40 cm. So, yung last step natin guys, the third one is to the total. So, is i-add lang natin to guys, 128 cm squared plus 40. So, 168 cm squared. Ito na yung ating total area guys. So, maraming salamat sa panonood. Hello guys, I'm Sherwin Razon, and our topic for today is all about parallel axis theorem. So, we'll now make a little calculation. Let's draw an example of our rigid body. And let's take the center of mass, and let's consider an axis that is going perpendicular to the center of mass. We can take of the object is rotating about that axis. And now, let's consider an axis to a different point, but also parallel to this axis, separated by a distance d. And the key result that we want is at the moment of inertia, about an axis passing perpendicular to the plane of the object through the axis S, is equal to the moment of inertia about an axis passing to the center of mass. Notice this parallel axis plus the mass of the object times the distance between the two parallel axes. And this is a result that is very useful when calculating moments of inertia. Of course, we could calculate the moment about any axis we wanted. For example, we know that a rod of length L that the moment of inertia to the center of mass was 112 m, and let's call the length of the rod L. So we have a length L, and let's assume it's a uniform object, and we'll calculate a moment of inertia through an axis to the end. And so in this case, D is equal to L over 2. And so about the end axis is 112 ml squared plus the mass times L over 2 square, and at 12 plus a quarter is 1/3 ml squared. And that means that all you need to know is the moment to the center of mass, and you can calculate the moment through any other axis. Very useful theorem called the parallel axis theorem. Now, as I said, we can calculate the moment S, and just to show you very quickly, if we pick S here and we pick our little dm there, and we have a distance x, then the moment about S, let's say that dm is equal to the total mass divided by the length times some little distance dx, then the moment is dm times x squared, where x will give this an integration variable. X prime goes from 0 to x prime equals L. And so, we have for our dm over L dx prime. Remember, that's our integration variable. And we have x squared, so that is x prime squared. And this is just the integral of x cubed over 3. So we have 1/3 m over L x prime cubed. Evaluate from 0 to L, and that comes out to 1/3 ml squared. And that's in agreement with the parallel axis theorem. Thanks again for listening. Bye. Hello guys, I'm back again. And my last topic is all about moment of inertia, product of inertia. My example is all about moment of inertia of shaded area about x-axis. So a square is given there. So the CB is a square, and the OAB, this is a quarter part of the circle. By subtracting quarter part of circle from a square, so we got this shaded area that is clearly mentioned in the question itself. So if you want to find the moment of inertia of shaded area, you should know moment of inertia of square and quarter part of circle about x-axis. If you know that relation, so then this problem is very easy. So if you want to have this shaded area, you need to consider a square first. A square of dimension gave, so this is the x-axis and the y-axis. This is the y-axis and the x-axis. Consider this one as geometry 1. And this is the radius. From this geometry, you need to subtract a quarter part of a circle. Subtract the quarter part of the circle. The radius. So of radius r, so then you will get the moment of inertia of the shaded area. They both x-axis. So moment of inertia is denoted with capital I. As we are doing this respect to x-axis, so denote with suffix x. Capital I and denoted with suffix x. So actually, moment of inertia for rectangle with about base axis, we know that, so it means nothing. But it is actually based into height cube divided by 3. For rectangle, so when you consider square, the square here, so base is equals to radius here, and the height is also equal to radius. So then it is r into r cube. So then it is r to r cubed divided by 3, which is nothing but r power by 4 divided by 3. So this is the relation for square of dimension r. So this is the area of moment of inertia over a square of dimension r. Next, the moment of inertia of quarter part of circle about x-axis is pi r power to the fourth divided by 16. So pi r power to the fourth divided by 16. So direct substitution of relation here. So take r to the fourth is common, and then 1 by 3 minus pi over 16 is equals to, when you simplify this one, we get 0.14 r. 0.14 r to the fourth, and that's all. Thank you.